Hello everyone, welcome to my channel, the Civil Channel 25. Now I'm doing the video on continuation of the previous video. See, we have finished up to normal stress and shear stress. What is the normal stress and what is the shear stress? And next, see, in any material, stresses are broadly classified into two types, that is normal stress and shear stress. The resultant stress at any point is given by sigma resultant is equals to under root of sigma square plus tau square, and tan pi is equals to tau by sigma. This is very important formula. And next, angle of obliquity is denoted by pi. Angle of obliquity is defined as the angle between the normal stress and resultant stress on any plane. See, for this angle of obliquity, the formulas also, the problems also given. They will be giving the tau and sigma, and they will be asking to find the what is the angle. So we have to substitute the values in this. And next one, based on the dimensions, there are two types of the stresses, that is conventional stress and true stress. Conventional stress is also called as engineering stress and also called as nominal stress, and true stress is also called as actual stress. What is the difference between this conventional stress and true stress? First point is, engineering stress is calculated based on original dimensions, that is before load application. This will be done before the load application. This is known as conventional stress or engineering stress or nominal stress. And see here, true stress means true stress is calculated based on instantaneous or actual dimensions. See, here before load application and here instantaneous or actual dimensions. This is known as true stress. And engineering stress is represented by sigma E engineering is equals to P by A naught. And true stress, A naught means original cross section area here. A naught represents original cross section area. And true stress means sigma true is equals to Pi by Ai. Like instantaneous, Pi is instantaneous load and Ai is instantaneous area. And see, conventional stress can be calculated theoretically. It cannot be, this true stress cannot be calculated theoretically. This conventional stress, it is used to study the elastic behavior of the material. It is used to study the plastic behavior of the material. This is true stress. Here the Hooke's law is valid. Hooke's law means within the proportionality limit, the stress is directly proportional to strain. Here in conventional stress, this Hooke's law will be valid, and in true stress, simple power law is valid. Sigma T is equals to K epsilon T power N, where K is equals to strength coefficient, N is equals to, N represents strain hardening exponent, and N will be 0 to 1. Relation between the true stress and engineering stress. This is very important formula. Sigma T, sigma true stress, like T represents true stress, is equals to sigma E is equals to 1 plus epsilon E. And also this is written as epsilon T is equals to log N 1 plus epsilon E. Coming to the stresses on inclined plane, there are stress transformation equations, like two equations are there, that is sigma theta is equals to sigma cos square theta, and tau theta is equals to sigma sin theta cos theta, that is sigma by 2 sin 2 theta. These two equations are stress transformation equations. Stress transformation equations. Next, coming to the conclusions. First one, stress is a second order tensor quantity. And next, we can determine the normal stress and shear stress on any oblique plane passing through the point of axially loaded member. When the normal stress acting on the cross-sectional area and the location of the oblique plane is also known. And next, stress at point is used to define the different stresses acting on the plane that is mutually perpendicular that passes through the point. And also stress at the point can be represented by the graphical representation also, and also graphical representation, and also the matrix representation also. See, this is the graphical representation. Sigma x, sigma y, sigma z. In three directions it is there. And here see tau sigma x, tau xy, tau xz. Here sigma y, tau yx, tau yz. Here sigma z, tau zx and tau zy. And coming to the matrix representation is also known as stress tensor at the point. Sigma 3-dimensional is equals to sigma xx, tau xy, tau xz, tau yz, tau sigma yy and tau yz, tau zx, tau zy and sigma zz. This matrix is called as square and symmetry matrix. The symmetry of the matrix is obtained from the moment equilibrium condition also. And one important point we have to note down. To keep the point under the equilibrium condition, every shear stress develops a complementary shear with equal magnitude but opposite in the direction. And this is called as the complementary shear stress or cross shear. Next, what is the plane stress problem or biaxial stress problem? Plane stress problem means if the stress is developed on any one of the mutually perpendicular plane. Any one of the mutually perpendicular plane passing through the point is assumed to be 0. I'll be showing the one example also. Then it is known as the plane stress problem. Understand? See, the stress will be developed mutually perpendicular to the plane passing through the point and it is assumed to be 0. Let us assume that normal stress developed on the z phase is 0. Like sigma z is equals to 0, we have to assume now. Sigma z is 0 and tau xz, tau xz, tau zx, tau yz, tau zy will be also 0 now. Then the plane will be in 2D. Sigma 2D is equals to sigma xs, tau xy, tau yz, tau yy. See, if these values are 0, these all values we have to substitute here. Then we will get sigma 2D is equals to this matrix. And see, the number of independent stress components required for a 3D element is 6 into 3 normal stress components that are perpendicular plus 3 shear stress components that is parallel. And number of independent components required for 2D element is 3. That is 2 normal stress components that is in perpendicular direction and 1 shear stress component that is in parallel direction. Now we will be learning about the strain. First of all, we have finished about the stress and now strain. Strain means the measure of deformation caused due to the external loading. External loading is called as strain, and it is the ratio of the two quantities with the same units. And this for this strain there are no units, and strain is of two types, that is shear strain and normal strain. Shear strain means the shear strain is due to the shear force, and it is also defined as the angular change between any two mutually perpendicular planes. It cannot be determined experimentally, and shear strain is denoted by theta is equals to pi by 2. Pi is known as pi denotes angular deformation here. And I have told you strain is of two types, shear strain. We have finished about the shear strain, and coming to the normal strain. This normal strain is due to normal load, and also under the action of the normal strain, this under the action of the normal stress, this strain will be developed, and it causes only the dimensional changes only. And the normal strain is of three types: longitudinal strain, or linear strain, or primary strain. Understand? And this normal strain is again is of lateral strain also. Three types I have told you, longitudinal strain, lateral strain, and volumetric strain or dilation strain. Understand? And next we will be learning deeply what is longitudinal strain. Longitudinal strain means the strain measured only along the applied load direction. It is considered as primary strain also. Lateral strain means the strain measured across the perpendicular to the applied loading direction. This is known as lateral strain. It is considered as secondary strain. Volumetric strain means ratio of a change in volume to original volume is called as volumetric strain. And we have to remember one point: Every longitudinal strain is associated with two lateral strains. Every longitudinal strain is associated with two lateral strains, and the nature of the longitudinal strain and lateral strain are always opposite to each other. Understand? Always opposite to each other. And I have told you the shear strain means theta is equals to pi by 2, no? And again coming to volumetric strain for different x sections. Volumetric strain for different x sections. First one is a rectangular x section. Actually for every section there is the derivation, and after that the formula will be the formula is there. That is no need. That explanation and derivation is no need. I will be telling the formula directly. For this rectangular x section, see, EV is equals to x plus y plus z. Volumetric strain is equals to epsilon x plus epsilon y plus epsilon z. And coming to the second case, that is cylindrical case. This is cylindrical, and next one is sphere. Cylindrical case. Here volumetric strain is equals to E linear plus 2E lateral. Understand? In competitive exams and in some bits also, they will be asking that what is the formula for what is the volumetric strain for rectangular x section. This is the answer. And what is the volumetric strain for the cylindrical section. And the next one, third one is for sphere. For sphere it is this is the sphere, right? This is strain. For sphere volumetric strain is equals to 3E linear. Understand? Okay. Next one, coming to the strain tensor. Strain tensor means epsilon xx, tau xy by 2, tau xz by 2, pi xy by 2, pi xz by 2, pi yz by 2. This pi is pi represents the angular deformation. And see, epsilon yy, pi yz by 2, pi zx by 2, pi zy by 2, and epsilon zz, ezz. This is the square and symmetry matrix. This is called as strain tensor. Next, coming to the Hooke's law. Hooke's law. Hooke's law means within the proportionality limit, the stress is directly proportional to strain. See here, within the proportionality limit, the stress is directly proportional to strain. Sigma is directly proportional to E longitudinal up to proportionality limit, and sigma is equals to here this is the constant and this is longitudinal. See, Hooke's law means this is the stress and this is the strain within the proportionality limit. There are the limitations of the Hooke's law, that is, it is valid under uniaxial loading up to proportionality limit. Uniaxial means only one load, and it is valid under pure shear loading condition only, and it is valid under hydrostatic state of stress condition only. And see, we have to remember one point. See, hydrostatic state of stress condition is used to describe the normal stress, tensile or compressive stress with equal magnitude in all directions with the same nature. Understand? And coming to the elastic constants, there are four elastic constants. This is very important. Elastic constants. Actually, what is the elastic constant? First, elastic constant is used to determine the nature of strain theoretically, and elastic constant is used to build stress and strain relationship within the proportionality limit. And next one, elastic constants are constant for given material and using them in working stress method only. See, And next it is applicable up to the proportionality limits. For homogeneous and isotropic materials, there are 4 elastic constants I have told you. First one is Young's modulus. It is represented by E. And second one is shear modulus. It is represented by G, N and C. And third one is bulk modulus. It is represented by K. And fourth one is Poisson's ratio. It is represented by mu r 1 by m r. Understand? See, Young's modulus and Poisson's ratio are independent elastic constants. See, Young's modulus and Poisson's ratio are independent elastic constants. And see, this shear modulus and bulk modulus are dependent elastic constants. Understand? Now, what is Young's modulus? Young's modulus. What is Young's modulus? E. Within the plastic limit, normal stress is directly proportional to longitudinal strain. Normal stress sigma is directly proportional to E longitudinal. Sigma is equals to, this is the constant, and E longitudinal. So, Young's modulus is equals to sigma by E longitudinal. This is the formula for the Young's modulus. Sigma megapascal. Understand? So, this E can be defined as the intensity of the stress causing 1 unit longitudinal strain also. And one thing we have to remember, this is the graph, that is stress, this strain, and this is the proportionality limit. This one proportionality limit, and this one another proportionality limit. This is E1, this is E2, and this is E3. Here, see, this is sigma and E longitudinal. From graph, we can tell that, slope is equals to sigma by E longitudinal. That is Young's modulus, no? So now, from this, we will be telling that as slope decreases, Young's modulus also decreases, but deflection increases. Understand? And that is the slope of the shear strain curve within the proportionality limit is also known as modulus of elasticity. And see, for a given value, E is directly proportional to 1 by E longitudinal and proportional to 1 by, see, from this, here Young's modulus increases, slope increases, and strain decreases, deflection decreases. Understand? And Young's modulus is used to determine the longitudinal strain theoretically, and it is non-zero positive value, constant for given material. And the units of this is megapascal. See, for different materials there is different Young's modulus. Very important one. See, Young's modulus for steel is 200 gigapascal, and for diamond is 1200 GPa, and for rubber is 10 GPa. This is very important one. And for copper is I think for copper 120 GPa, and for bronze it is 80 GPa, and for brass it is 100 GPa. And next last one is aluminum. For aluminum it is 70 GPa. And next one, we have finished about the Young's modulus, and next elastic constant is shear modulus. Shear modulus is denoted by G or N or C. Shear modulus means within the plastic limit, shear stress is directly proportional to shear strain. Shear stress means tau, and shear strain means pi. This one, tau is directly proportional to pi. Tau is equal to g theta and g is equals to tau by pi. Understand? This is the shear modulus for given value of tau here. As g increases, 1 by pi decreases. So as shear modulus increases, pi decreases, and shape distortion decreases. This is used to determine pi theoretically, and units of this is MPa, and it is dependent and calculated indirectly. Next elastic constant, we have finished shear modulus, and next one is bulk modulus or volume modulus of elasticity or dilation constant. Bulk modulus or volume modulus of elasticity or dilation constant. Understand? This is represented by K, and see, within the proportionality limit, volumetric stress is directly proportional to volumetric strain. Volumetric stress means sigma V, that is sigma that is directly proportional to EV, and sigma is equals to K EV, and here K is equals to sigma by EV. This is the bulk modulus, and K is used to determine the volumetric strain or change in the volume theoretically.